We're just going to be talking about a simple antenna you can build at home for about 30 bucks in parts, and then a few tools, nothing too fancy though. So this is one of the first antennas I built when I was a tech, and then it's timeless and it's really strong and efficient. So before we get started, I'm going to point out a couple things about this one. This guy. He makes and sells Jpoles and on a website on eBay, and I'm just going to point out the way he's got the coax fed and the way he's got it mounted with hose clamps. We're just going to talk about that later. He's got lots of options for customization. So a little bit about myself. I started in CB for off-road, and if you know anything about CB, it's pretty terrible, including the people who use it. So ham radio has it's a lot more efficient. You get a lot better signals, and I really got interested in the way antennas work and propagation and everything like that. So studied up. I got my technician in March 2016, and I took general just under a year ago, and I was one question away from failing each time. So if you're afraid, you feel like you don't know everything, just go ahead and go for it. You might get lucky. So this is my Festivus pole with a simple vertical. This is a portable setup I tried in my backyard. And this is my current setup. I live in a tiny home, so these are my solar panels. I've got a little rubber duck for 2 meter, and this is a 40 meter ham stick. 2 meter band covers 144 megahertz through 148 megahertz. For calculations, we use the midpoint, 146. In a vacuum, electromagnetic waves travel at the speed of light, which is close to 300 million meters per second. So wavelength equals the velocity in meters divided by frequency in hertz. So lambda, the symbol for wavelength, equals 300 megameters per second divided by 146 megahertz. Gives us approximately 2 meters, and that's why it's called the 2 meter band. This is my first 2 meter radio. It's a Yaesu 2800R that worked really well until I spilled coffee on it. So hertz stands for cycles per second. So one cycle refers to one full movement through the wavelength, peak to trough. So we're starting here, going down and back up, and that's a wavelength. So on 2 meters, it travels 2 meters, 146 times per second, going up and down through the waves. The radiation pattern of a vertical antenna, is mounted up and down. Then you have horizontals. It's your different modes of polarization. So vertical looks like a donut, the way the signals come out of there, and they can be different shaped donuts. They can curve up or go straight out or be really round. This is representing a dipole, a vertical dipole in a vacuum. Transceiver modulates an input into energy on a determined frequency. And it typically amplifies it along the way. So you speak into the mic, or you key your Morse key, or you use a digital mode, and then the radio turns that into a signal that can be propagated through the antenna. The antenna is fed down the feed line, reaches the antenna, it excites and vibrates the field vectors in the surrounding space, either horizontal or vertical. So that's that polarization I was talking about. It doesn't matter as much on HF because HF usually bounces off the ionosphere, it gets refracted, and then it's polarized every direction. But 2 meter, when you're talking simplex point to point or duplex, you're trying to hit a repeater. That repeater is going to be vertically polarized, and you're going to want to also be vertically polarized. And you're mostly going to be on this blue. This is the magnetic field vector, the H vectors, and then the horizontally polarized are going to mostly excite this E vector, the electronic side of things. Other antenna characteristics that are really important. this is from the MCRP 6-22D. This is a really excellent Marine Corps manual on antenna basics and fundamentals, and it's written for Marines, so it's like between a second and third grade. So radiation fields and patterns, polarization, directionality, resonance, reception, reciprocity, impedance, bandwidth, gain, and takeoff angle are all important things around the design and installation of antennas. All antennas will be a compromise of these different fundamentals, as well as space. If you've only got like a certain size backyard, or you live in an HOA, you can't have a 200-foot tower, and then cost. We could all buy the, there's a co-band HF portable vertical. It's only 8 feet tall, and it only costs $3,000 with the the Invis kit. But yeah, so but NGOs and people far out in Africa use those on their Land Rovers, but not really practical for when you're driving around Springs and you've got mountains, then you just need a direct line of sight, which isn't hard to find. So they're all a compromise between these different requirements. As a tech, after considering safety, you just want to get on the air. So get something cheap, easy. You don't have to spend a whole lot of money. You don't have to spend something specialized or buy something specialized, even though we do have the ham radio outlet in Aurora. They'll try to sell you, $3,000 worth of stuff as a technician. And as you gain experience, you can find out what you want/need rather than just buying the latest and greatest. So reasons to build your own Jpole, specifically. You can practice antenna fundamentals, learn new skills. They're cheaper than a lot of other verticals in the setups, and it's fun to do, I think. This is another kind of Jpole. This is called the Crazy Cactus, and so it's got this band of copper tubing that's bent. These are isolated. There's wood in between these, and then so this copper connected is what runs it through, and so this is for dual band. So some other kinds of simple antennas. A dipole is one of your most common horizontal antennas. You have your coax coming in, your center conductor is going to go one way, and your coax shield is going to go the other way. Each of these is going to be a quarter wavelength. You're going to have a half wavelength total, and you can make these as expensive and fancy as you want, or as cheap as you want. Another one is a quarter wave ground plane. So it's basically a dipole mounted vertically, and for the shield, it creates a ground plane with these pieces going out and downward, 45-degree angles. And these are all quarter wavelength as well. So a Jpole is it's a dipole mounted vertically, and then it's folded. And it's a full wavelength long. So you got a half wavelength here, and then you got a half wavelength going down and bending back upward. So this tall part is called your radiator, and this short part is called your reflector. Another configuration for a Jpole is this. I forgot what it's called. But it's bent on itself, and so you get more gain by having the radiator bend on itself, and it can be more compact. And you can do this. There's easy ways to find online of guys taking the window wire. It's just two pieces of wire connected with rubber in between, and that's a really good one for portable, like emergency setups or setups on the air if you're doing VHF SOTA. And then it's hard to see. We were messing with a projector earlier, couldn't get it to work right. But this is how you're going to feed your coax into your Jpole. So you've got a chassis mount SO239. That's just your normal UHF connector. You soldered a solid copper wire into the center conductor, and then you solder this chassis onto the reflector. And then the center conductor goes to the radiator. That's the tall part. So that's one way you can do it. I'm going to show you another way with just a slightly different hardware configuration where the connection is going to be down here in the bin. So, all right, so calculations for 2 meters. We touched on this earlier, and this is a technician level question as well. So a half wavelength is going to be 150 divided by megahertz. So that's going to give you and we convert that meters to feet. That gives us 492, and then we accommodate for the K factor. So that 300 megameters per second, that's in a vacuum, and then that's not accounting for the way it slows down going through the copper or the wire. So we multiply that by 0.95 to take out a 5% speed loss. We get 468. 468 divided by 146 is 3.205 feet. For a half wavelength, we want a quarter wavelength, so we want 1.60, 9.3 inches. We're going to round that down to 19.3. We're going to round that down to 19.25 inches. So your quarter wavelength is going to be 19.25 inches. We're going to use that to do all of our measurements and cutting. Some tools you'll need. You need a simple propane torch. You can get the fancy MAP gas that plumbers use. It burns a little bit hotter. I've got a video that's going to show you the soldering, but you don't have to get fancy. You can just use your regular camping propane bottle and the torch that attaches to that. Strike it with a lighter, or you can get one of the magnesium starters. Little tape measure. You can use a hacksaw, but these tube cutters are pretty cheap and they're pretty cool. I was gonna cut up some pieces for you guys, and I was in a rush. I got a copper grounding pole instead of copper pipe, which is a little bit harder to cut. Yeah. But you put this on there, twist it down, you spin it around a couple times like that, and then you gotta tighten it down a couple times until you get all the way through the wall. But those are pretty simple to use and makes the job a lot easier. Then you'll want some solder, preferably lead-free. This is for designed for copper pipe. It's because you're going to want a strong mechanical connection as well as a strong electrical connection. But that guy I showed you earlier, KB9 BBR, who sells the Jpoles on eBay, he uses rosin core solder and obviously gets by just fine with it. You want to use flux. We'll talk about that in a second. You want to use something to clean your pipe really well, get all the impurities off, and that's going to give you a nice surface for the solder to adhere to, and the flux also burns off impurities. And then you want some extra hands, or if you can just use a bench vise or a pair of pliers, something like that. And okay, so this is our configuration of the main joints that we're going to use. So we've got our reflector. We want it to be 19.25, but we're going to have an end cap on it, just a copper half-inch end cap, and also the joints in here are going to lengthen it. So you'll cut it at 19 inches. That's your part A. You'll have your radiator. It's going to be, like we said, it's a half wavelength for the radiator and then a quarter below that. So it's going to be 19.25 times 3 minus a quarter for the addition of the cap and the T junction. So we're going to do 57.5 inches, and that's going to be going up here. A 1 3/4 inch spacer that just goes right in here. 2 T's, these copper T's that hold everything together. Your mast, you can decide how long you want that to be, just depending on how you're going to mount it. If you're going to mount it with hose clamps or conduit clamps, the way I'm going to show you. And then your end caps, which I've got on the table if you want to come look, they're just going to keep water out if you're going to leave this set up as a base station. Your chassis mount SO239 is going to go here. Got more detail on that in a second. So this is the other way of showing you where your chassis mount can go here and just go across, or to keep the strain off of the coax. That's the main reason for doing this setup. You run it into, you get another T instead of a 90-degree and just run it straight down. And then this is my preferred way to mount it. You get a threaded 1/2-inch pipe adapter and a 1/2-inch flange. These are either galvanized steel or black iron. These are the 2 most expensive parts after the pipe. But you screw this onto your deck or your roof or anything like that, and once you have that there, then all your, if you want to build multiple Jpoles or other setups of antennas, you could put this same adapter on each of them and switch them out pretty easily, and it's a pretty solid connection. And so that is going to go into the bottom of your mast here. And so here's some detail on how the center conductor is fed for this setup. So this is going to be the hardest part, but it's still relatively simple. You drill a small hole here, just slightly bigger than the size of the wire you're using. You run your wire in first. After this joint is soldered, this joint is soldered, after you've done all this, you run your wire in here, run it down. You want a really long length so you can get away from the pipe. You solder that to the center conductor on your SO239. Then you heat this pipe up really hot, being careful not to melt your wire. And you also have to be careful with this SO239 because they do have ceramic insulators and they have bakelite insulators. Those are what you're going to want to use for this. But if you get a plastic one, it's just going to melt as soon as you touch it. But you still have to be careful, even with the bakelite ones, they still melt eventually. But you apply most of your heat directly to this T, and then once it's hot enough that it's melting the solder, you push it up, and then you just run your solder all the way around this ring. And so then the shield is attached to the chassis mount, which is attached to the reflector, and then the center conductor is running up out of this hole into here. When you're tuning it, you're going to want to buy or borrow an SWR meter, and you're not going to want to solder this joint yet. You're going to want to use a hose clamp or something to hold the wire to the radiator until you find the proper height to give you the best SWR signal wave ratio. And then once you've found where that's going to be, mark it, heat the pipe up, because if you tin this wire, but heat the pipe up, and then you just solder it in place and wrap it with like just a coax tape to prevent corrosion. So the prep work is the key. The sanding all the impurities off, removing the oxidation, and then also afterwards removing the leftover flux, because that stuff corrodes really easily. Using the flux is pretty much mandatory. It burns off impurities and it aids in the flow of the solder into the joints. You apply the heat directly to the metal. You don't heat the solder, just like we're doing on any other normal electrical soldering. and then allow the joint to cool fully before moving. You don't want to get a cold flow joint where it got interrupted. And your goal is a strong mechanical joint in addition to a sound electrical one. So, we're actually going to KB9 VBR, he makes that antenna on the first slide. He also makes this one. This one, he's feeding the coax in the correct way. And it's interesting that the other picture is his flagship model, and he feeds the coax in the wrong way. So you want, this side is going to, think of this side as your positive or your negative. The reflector is going to be your negative because the shield is going to be attached to that. And this side is going to be your positive. So all the signal that's going to excite the airwaves is going to be in the positive radiator side when it's fed the right way. If you feed it the opposite way, if you feed it like this, where your reflector has the center conductor attached to it, all the signal is going to hit this point. It's going to negate itself here, and then this is just going to be extra ground. So you're going to have a low SWR because it's still a solid design, and it's not sending energy back into the radio, but you're not going to have as strong of a signal. So there's just have it go the other way, where your long part is going to have your center conductor. So, then you want to put a little strain relief in this. So after you got your coax hooked up, just give it a little slack in there and strap that down with either a wire tie or a hose clamp or something like that. So a little bit short, but do we have any questions? Yes.
What gauge wire do you use coming off the coax?
Probably like if you're using solid, probably like a 10 or a 12.
Okay.
When you're measuring for your lengths of your elements, do you measure from like the end to the corner of the joint, or do you like from the end to the center of the joint?
Yeah, your end result is going to want to be the desired measurement. So the measurements I showed were the measurements for cutting, and but your end result is the one that you're going to go towards. Does that answer that?
Is it measured to the center?
No,
to the
end.
corner of the joint.
End to end. So. Yes.
I have 3 questions. How much efficiency do you get out of this Jpole over a standard vertical? Just roughly. I mean, what's the?
It's pretty efficient because it's got its ground plane built in, so that's what makes it a really good base antenna. Instead of running a bunch of radials or doing a ground wave where you.
So like, let's say a magnetic mount on top of a car, how much more efficient is this? Not any more efficient at all, just you don't have to have a ground plane?
It's probably not best for a mobile, so it's a.
Well, yeah, obviously it's not a mobile, but
Right.
like if you took a vertical antenna sitting on a magnet mount on a
Right.
vehicle, is it pretty much similar? You're just
I think Bob's got a better.
Yeah, let me take that. The way I think of it is, the Jpole is fundamentally a half-wave radiator. And so you're gonna get, like compared to it, if you hung a dipole, the dipole's also half-wave, like
Yeah.
vertically. So those two are gonna perform the same. Sometimes people will claim they're getting a little bit of gain out of the Jpole. I don't believe it. I think it's a half-wave radiator. And then you go, okay, what other antennas do we know about? Quarter wave radiator with a good ground plane, like roof of your car, right? With nice ground plane quarter wave. That also has the same performance as a half wave radiator. You're getting reflection off the ground plane. So Jpole, half wave vertical, quarter wave with ground plane. Those are all equivalent performance.
Okay.
And then after that, you go, well, how do I get some gain? Well, then you start building more exotic antennas.
And then another question is, You'd mentioned earlier on that vertical or horizontal polarization doesn't really matter that much for HF. Does it matter at all? I mean, when you're doing kind of reflection, is there a significant difference if somebody had a vertical and you had a dipole antenna?
I'm not an electrical engineer, but
So you got
For us-
So locally it will, if you're doing skywave propagation, it's
Yeah.
not gonna matter.
Okay.
But if two guys are across town and they're just trying to chat locally, you'll get some polarization loss if
Okay.
one's horizontal, one's vertical, but that's not usually what we care about on HF though, right? We're usually
Right,
going
yeah.
for the distance.
Then the final question is, if you put up something like this, a short J-pole at 2 meters, is that inherently dangerous if you have lightning? Is the fact that the antenna's out there, does it actually somehow absorb electromagnetic energy, where it's like sucking in lightning, not maybe a direct strike, but enough energy that you could potentially damage something? Or do you have to really get to a much higher antenna before that's an issue?
it's always got that possibility because it's basically a lightning rod. So
Yeah,
wait,
but at 2 meters, is it really that big of a deal?
it's a big deal in any situation.
Okay,
So
You know, all antennas should be grounded.
okay.
The shields of all antenna systems should be grounded to protect against lightning.
Well, it's, the grounding
There's
is,
always a chance, even if it's not extending up 100 feet, there's always a chance of lightning
the grounding
hitting
isn't an issue. It's
any
really-
sharp object poking up into the sky.
I'm just wondering, like, if you're grounding a big, huge antenna up in the air and you go through all those issues that we learned in the class to put 3 grounding rods and, make sure there's no square, I mean, is it just maybe having a small grounding rod and ground better than nothing? Or do you
Yeah,
have to
I
do
mean, the
full
minimum
feeding?
grounding configuration
Yeah.
would be a single 8-foot ground rod,
Okay,
and probably a number 8 wire going from the ground rod
Okay.
to a firm connection on the shield of your system.
okay. Yeah, because that would be
As short a path as possible, because the longer that ground wire is, the more inductance you get. And a lightning strike has relatively high frequency components, and the inductance will cause a significant impedance to ground.
Okay.
So you want to try to keep that as short as feasible.
Thank you.
In other words, wherever the connection point to the shield is, keep
Yeah.
that number 8 wire connection.
Okay.
You could use number 6, I use number 6 in my
Okay.
system, but keep that as short as possible.
Can you just use grounding strap too? Does it matter whether you're using a grounding strap? Is that better? Would a grounding strap be better than?
Yeah, you might want to check, if you got a simple grounding strap that's exposed to the weather like that, you probably want to check it every year to make sure it's not corroded.
cool.
And the more ground rods, the better. As Stu's system illustrates, I don't know if anyone's ever seen Stu's system, maybe he'll talk about it on Monday. Stu's got, I don't know, it's over a dozen ground rods, right? Your grounding system surrounds your entire house, does it not?
Well, it used to, but I had my driveway redone back in September,
I see.
and it don't no more.
So I'm doing, your first VHF station kind of presentation this afternoon. I'll talk a little bit about grounding, and then Stu's talking about HF stations. He's going to talk a little bit more about grounding. Unfortunately, we could talk all day about grounding, and we still wouldn't have it covered. So we're kind of giving you a light touch, but we will hit that a couple more times.
Well, this answers my question. I mean, what's the minimum? Because obviously.
The
if you got
minimum
big-
is
big
one
antenna in the air-
8-foot ground rod driven all the way in,
Okay.
with as short a number 8 wire connection as possible to the shield of your system. Right, ideally right where it enters the house.
You got another.
Where's the best place to find one of the coax connectors?
Amazon. You can get a 5-pack for $7 shipped. Amazon or eBay. And look for the Bakelite or ceramic. Or if you're ever passing through Denver, the ham radio outlet is a really cool place to check out if you haven't done it.
The video that you showed, which I guess is from YouTube,
Yeah.
can you tell us what that video was?
Yeah, and if you guys want to, I can give you, you can give me your email and I'll send you a file of that Marine Corps manual and this PowerPoint and the articles I used. But it's, you can just look up soldering copper pipe or brazing copper pipe and you'll find plenty of options. That was just the shortest quickest one.
But we'll get all these slides out on the club website after today,
Yes.
so you can look at them there.
I have a question about diameter of pipe that you choose for this.
Yeah.
Is, other than like weight, cost, and things like that, is it better to have a thinner copper pipe, a wider, or doesn't it matter?
Yeah, so half inch is just a good compromise, especially if it's your first one, but I've also built 3/4, and you could use a different K factor like we talked about, but it's really not important with that small of a difference. And but going bigger is going to give you a stronger pipe. So if you know it's going to be a base antenna and you're going to leave it up all the time, and we have high winds here, then that'd be a great option. So,
Good. That's right.
in the back.
So similar, that's what I was going to ask as part of a two-part question, but I want to confirm. So what you said is it makes a stronger antenna, but not, it doesn't change the signal that comes out of it? And so is there a difference between a copper pipe and a wire other than just the strength of the antenna in terms of the signal?
Yeah, it would be a negligible difference, especially on VHF.
Okay. And the second part then, is there any difference in what, excuse me, what power is appropriate for a copper pipe versus a wire antenna?
That's a good question. I can't give a definitive answer, but some of the stuff I saw when I was researching for this was talking about up to 300 watts, which is, unless you're using an amplifier in VHF, then that's not going to be, it's going to be above and beyond.
Yeah, I think the short answer to that question is there's not really it's not gonna make any difference. You don't need to put more power into the Jpole to be just as effective as, you know, narrow single wire antenna that you may use on HT or anything else. But it can probably handle a lot more power if you are looking to use an amplifier and boost it.